Welcome to Chapter 13. We're going to learn about radioactivity and the strong nuclear force. We'll start by talking about radioactivity, the types of radioactivity, where radioactivity comes from, and then we'll talk about the atomic nucleus and that strong nuclear force that holds a nucleus together. So radioactivity involves radioactive decay of some sort, which is where part of the nucleus is ejected or added to. So generally the radioactivity we're sensing is where it's emitted. The Earth actually has a lot of radioactive elements, especially in the middle, and when a volcano erupts, quite a bit of radioactive material spews out of it. So we think of radioactivity when we think of atom bombs, and we think about it when we think about the radiation that you get in medical treatments and things like that. But actually the Earth itself emits a lot of radioactivity on a daily basis. So there are several types of radioactivity. We're going to talk about three of them. The first is an alpha particle. An alpha particle has 2 protons and 2 neutrons, so it's basically a helium atom, and it's ejected from the nucleus. And it would have a 2+ charge unless it picks up electrons along the way. Electrons are fairly easy to pick up, especially when they're leaving an atom that now has 2 extra electrons because it's emitting helium. But they're often ejected with a lot of force. If you have an alpha particle coming towards you, it can be stopped by a piece of paper. So because they're so massive, they can be stopped fairly easily. Just put a piece of paper in front of yourself and you've blocked it. Or have a layer of dead skin, which comes pretty naturally, and that will also stop your alpha particle. They have a large amount of kinetic energy because they're so large and because they're ejected at such a strong rate. They can actually cause a lot of tissue damage if they do get to live tissue. But once they've picked up those 2 electrons and they lose their kinetic energy, then they become harmless helium and they no longer cause damage. The place where it would be dangerous for you to be around an alpha particle is if you breathe it in or if it's emitting in your body, in your tissues. And the reason that's more dangerous is it's being stopped by things that might be DNA, things that are more critical that they stay exactly as they are. And we actually have a lot of ways that our body can fix these mistakes that happen when we get radiation, and that's a good thing because we actually have elements that are in our body that contain radiation, that are giving off radiation. And so when they give it off in our body, if it's an alpha particle, it can cause some damage, and our atoms have great ways of fixing the damage that happens, and that's good. Otherwise we would all have cancer at very young ages. The next one is a beta particle. Beta particles are smaller. They're basically an electron that is ejected from the nucleus. Now, if you think about it, your nucleus contains what? Protons and neutrons. Notice we didn't say an electron. The electrons are on the outside. So where is that electron coming from? Well, as it turns out, neutrons are made out of protons and electrons combined together. So a neutron can split in half and eject the negative charge and leave the positive charge in the nucleus, and you've basically turned a neutron into a proton, but the side product that shoots out is an electron, which is your beta particle. So the proton stays in the neutron, the electron leaves, and it has a -1 charge as it's leaving because it's an electron. You can stop a beta particle by the top layer of your skin or a sheet of aluminum. So you take a piece of aluminum foil, hold it in front of you, that stops it. Your dead skin can also stop it. And once they're stopped, they become a regular electron in the material they're in. And you've dealt with those before. If you take a balloon and rub it on your hair like stands on end. Or if you touch something, you get an electric shock. That's also electrons. So you've dealt with just harmless electrons going around. But when they're shooting out at that high velocity, they can do some damage. And once again, as long as it's on the outside of your body coming at you, you're good. If it's on the inside, not so good. Okay, well, having said this, that your body can protect you from alpha and beta particles coming from the outside unless you're breathing them in, well, why are we so concerned about these bombs that are emitted? And there's a couple of reasons. One is you get more radioactive material inside of you, but the one that kills you right off is not an alpha particle or a beta particle, it's a gamma ray. Now, gamma rays are high frequency electromagnetic radiation. No mass that we detect, kind of like light. We theorize that there's mass, but we don't see it because it's so small. It can be stopped by a sheet of lead. Now that's why when you go to the dentist, they put that sheet apron over you. They're blocking you from X-rays, which is a similar sort of thing to a gamma ray. These gamma rays can be stopped by lead, and it will penetrate all the way through the body and cause damage as it goes if you don't have that sheet of lead in front of you. So this is what, in the bomb of Hiroshima, this is what burned people alive, are the gamma rays. And then you get the radiation in all the plants and stuff. You eat the food, there's the long term showing up as you get the damage from the radioactivity in the environment. But the immediate killer is a gamma ray. So places that you'll find radioactivity. Rocks and minerals that come from the earth have a lot of radioactive isotopes, especially uranium, which has a very long half-life, so it's stuck around for a long time. If you live in a brick house, you actually are exposed to more radiation than if you live in just a wood and plaster sort of house. And that's because it has these rocks and minerals put into there. You'll also find uranium deposits that decay, and they form radon-222. And in the houses that are built nowadays that are really well sealed, you can get a buildup of this radioactive radon. Old houses, it just seeps through the walls and goes everywhere, and so there isn't so much of a problem there. Radon itself, pretty harmless, but if you breathe it in and the radioactive decay happens, then you can get some damage in your lungs or wherever it is that it is in your body. A fifth of your annual radiation comes from unnatural resources. So medical procedures, I've had cancer, they irradiated my head, my hair fell out. That would be an example of a medical one. They have others that do diagnostics. They have ones that treat your thyroid if it's overactive, kill some of the tissue there. So various things that they do for medical procedures. The old TVs had cathode ray tubes, and those were actually sources of radiation because they create the picture by knocking off your electrons. So that would expose you to radiation. Nuclear testing, this was really a problem a generation or two ago. People who lived downwind of where they did testing of your nuclear bombs ended up with a lot of cancer above the normal rates. So, for example, my mom's relatives lived downwind, and 6 of her 7 uncles had a really serious cancer. So that could cause some of the exposure. And then coal mining and burning is actually a really big contributor to radiation. Not as big of a problem in the United States so much anymore, but if you go to a place like China where they still burn a lot of coal, that's going to contribute to the cancer rates there. And your nuclear power plants do have radiation, but that's not released into the atmosphere. So we're not exposed to it unless there is a nuclear power plant disaster that releases nuclear radiation. And we did have a very major one of those called Chernobyl a while back that did release into the atmosphere, and the area where it happened is still uninhabitable, and they're still trying to clean up the mess from that. So when we're reporting radioactivity, there's a couple of ways that we do it. One is RADS. and that's radiation absorbed joules. So it's measuring the energy that's absorbed per kilogram of tissue. And the energy could come in various forms. It could be alpha particles, beta particles, it could be your gamma particles. That's just measuring those. Your REM is one that's built specifically for human beings because this is rotogen equivalent for man. So the alpha particle, if it's actually absorbed in, counts for 10 times what a beta particle counts for. And that's because the alpha particle has more mass, does more damage. And so the REM kind of lets you know how much radiation you've been exposed to by way of the damage it's going to cause. So lethal REMs is about 500 REMs. You have about a 50% chance of survival if you get exposed to 500 REMs. Radiation therapy, which is for cancer, they have over 200 REMs a day for a period of weeks. And this actually builds up problems in the body, and you get radiation sickness. Some people get vomiting, your hair falls out, you end up exhausted because there's so much tissue damage done that has to be repaired. And it's interesting how it works because it builds up. So the first little while that you're doing it, you're like, this isn't affecting me at all. And then the hair starts to fall out. And it's actually after they've completed the radiation therapy that the people are often the most exhausted because the body is really feeling the full impact of all those doses and having to do a lot of repair. The upside to that is because it destroys tissue, it does tend to destroy the DNA of fast-growing things the most, and fast-growing things are generally cancers. And so while it causes your hair to fall out, it also destroys the cancer cells. And so it can be a very beneficial thing in that way, and that's why we do it. Otherwise, there would be no point. Usually the amount of radiation we're exposed to is measured in millirem, 1/1000th of a rem. That's, you just walk around on your daily routine, eat food, being exposed to things around you. That's it. So minuscule compared to what you get in cancer treatments or what you get if you had an atomic bomb go off. Totally different ballparks there. But still, the millirem can cause damage and it will need to be repaired. So the average person is exposed to about 360 millirem per year. About 80% of that is coming from the sun, the ground, or the air, or from human tissues. In our bodies, we have potassium, which we ingest and need. If we don't have it, we have problems. And we have some radon. Both of those are radioactive, and they're going to be emitting radiation into the body that has to be dealt with as we have to correct the mistakes that happen from that released radiation. About 20% comes from non-natural sources. X-rays are the most common, which we get for dental things and things like that. And they've actually decreased those doses recently because they can record the radiation picture digitally, and that sensitivity has gone up, and so they actually don't hit us with as much X-rays as they did when I was a kid, which is great. Less chance for problems when they decrease that dosage. Nuclear medicine is so radiation to test things, radiation to treat things. Those are part of your 20%. And TV tubes, but now that we have flat screens, we don't have that, which is great. Cells have mechanisms to repair the damage caused by radiation, as I've already said. Often a highly damaged cell will just be killed. Your body destroys it. When it doesn't die or repair itself, then sometimes we get cancer. Radioactive tracers are an area of medicine. You have your nuclear medical technicians, and they will use radioactive material to watch how a molecule moves through the body or other living thing and see how you process something to see if there's a problem there. Those are called radioactive tracers, and they're often used in nuclear medicine to diagnose a health problem or to find cancers, things like that. And as they move through the body, they're going to emit particles, usually gamma, because you want them to come out of the body so that you can see what's going on. And the other things that you'd put in there, they wouldn't make it out of your tissue to be seen. So they then put these trackers around your body, and they're able to see where the gamma particles are coming out, and from that they can see where the tracers have gone in your body. The atomic nucleus is made up of protons and neutrons. And if you think about it, protons are positively charged. If you take two north poles of two different magnets and try to push them together, see what they do, with really good magnets, they're going to repel each other. Same thing happens with just a positive charge. If you take two positive charges and try to push them together, they're going to want to repel. So we have all these protons, they're in a close vicinity, really compact nucleus. And the question is, why are they just staying there? Why aren't they just shooting apart, just like your two magnets that you'd bring together are? And the answer is there is an attraction that balances out the repulsion. And that attraction is called the strong nuclear force. And it's an attraction that only happens over very short distances. And that's why your nucleus has to be so compact. They got to get really close together to get this attraction. And those distances are about 10 to the negative 15th meters. So really close together. You'll notice the periodic table stops at a point. They don't keep getting bigger and we don't keep adding elements. That's because the distance that we have there in the nucleus starts getting so far out that the repulsion takes over. And as the repulsion takes over, you end up not forming nuclei that are bigger. And so we stop forming new elements. This strong nuclear force counteracts the electrical repulsion and allows those protons to stay together. Now think about neutrons. If you were to bring a neutron near a proton, it could still have this strong nuclear force as long as they're close, but it won't have the repulsion because neutrons don't have any charge. And so if we take the strong nuclear force with some protons and throw in some neutrons, which don't repel but do attract, then they attract those protons without the counteracting repulsion, and we can build up a stability between the combination of the two that gives us a stable nucleus. And so we're able to build much larger nuclei that are stable than we would be able to build if it were just protons alone, because some of the particles are there with just attraction and no repulsion. So because those neutrons don't have the electrical repulsions, and they do have the strong nuclear attraction, the neutrons will stabilize the protons. And so the more protons you get, the bigger the nucleus gets, the more neutrons you'll need. So to begin with, you generally have like a 1-to-1 ratio of protons and neutrons as you're adding more and more. But when you get beyond about element atomic number 20, then you start adding more neutrons than you add protons. That's because the radius is getting so big that you really need things that don't have the repulsion in there, that do have the attraction to help hold the nucleus together. So when you get up to like uranium, you've got a lot more neutrons there than you have protons. And you're starting to get to a point where even so, it tends to be unstable. Neutrons themselves, if you were just build a nucleus out of neutrons, they would disintegrate. And so there's also a counteracting stability that those protons are able to give your neutrons. So neutrons just left by themselves break apart. They need the protons there to keep them together and stable. So this creates your size limit for the nucleus. The strong electrical repulsions eventually overpower the strong nuclear force because you reach a size where a proton on one side of the nucleus and a proton on the other side of the nucleus are not close enough together to attract with a strong nuclear force. And so they just repel. And as they repel, they want to shoot out of that nucleus. So anything above 83 protons is radioactive. Doesn't matter how many neutrons you add, they are radioactive. And this also creates a number of protons to neutrons that goes up, as I was describing. So for smaller nucleus, 1 to 1, but beyond 20 you get 1 to more than 1 of the neutrons.